In part 2 of module 22, I'll go through another example. This one's a sequence detector. So we're going to detect a sequence of bits on a single input. So for example, we could detect some sequence like 1, 0, 1, 1. And so our input, D, would be, here's our waveform with time on the x-axis, would be 1, 0, 1, the next clock cycle 1, and dot, dot, dot. So this is the same as exercise 1 from the week 14 practice exercises. So we're going to design an FSM that detects the following sequence of bits. In this case, we're going to detect this sequence, 1, 0, 0. A new value of D is given just after each clock edge. The output F, the found output, should become 1 every time the correct sequence of bits is detected. So this is called a serial input, D. And so here's an example sequence of what D could be. Again, kind of randomly putting these values. And so if we look at this sequence of bits, well, we have a 1, 0, 0 here, 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 again here, and here. So the F output, the found output, should assert after it's found that first sequence, the second, third, fourth, and fifth instance of that sequence, the 1, 0, 0 sequence. Okay, and again, remember that's a single bit input D, but in time it's changing. So it's a 1, and a 0, then a 1, and a 0, and a 0, and a 0, and then a 1, and a 1, and blah, blah, blah. So there's our waveform of that signal. So the first thing we want to do is draw the black box so that we're clear on what the interfaces are for this FSM. We always have the clock input and the reset input. So an FSM always has those two inputs. We need to be able to reset it to get it into a known state when it starts up. And then in this case we have the D input that has the data on it, the serial data. And then we have the F output. And now we want to draw the state transition diagram. So we always want to start with some state that has a reset input into it. So we always have this state, we call it the reset state, because at reset, when reset asserts, no matter what the current state of the system is, it goes into that state, the reset state. So we're going to call this the SR state, the reset state. We're going to call this the SR state. We could name it anything. Before we've used S0, S1, S2, S3. So we're going to name it, in this case, SR. So upon reset, it's going to go into that state. And now we're going to start looking for our sequence. Remember, the sequence we're looking for is 1, 0, 0 on the input D. And so first thing we do in any FSM is we draw the path of what happens when we successfully find the sequence we want or do the sequence that we'd like for the FSM to perform. And then after that, we'll look at the exceptional cases, what happens when we don't see that sequence. So in this case, the first thing we wanted to detect is a 1 on D. So D equals 1. We could write it like that, or we could also write it like this. And then we'll go to, let's call that the S1 state. That means if you're in the S1 state, it means we found the first bit of our desired sequence. Then the next thing we're looking for is a 0. So we'll say if D is low, in other words, D bar, then we'll go to let's call this the S10 state. So that means we found, if you're in the S10 state, we found the first part of the sequence, the 1 followed by the 0. Then the next bit we're looking for is another 0. So we'll make the transition out of that state, D bar. Again, I could also have written that as D equals 0. And we'll go into, let's name it the S100 state. So if we're in the S100 state, at that point we've found the sequence we're looking for, and we can assert the F output. So F is asserted in the S100 state. To avoid clutter, we only draw or list the output in the state where it's asserted. In all other states, F is 0. So that's the first step in drawing the state transition diagram. And now we need to tell what happens in the other cases. So from any given state, we need to know for every possible input what the next state should be. So right now, for example, in state SR, what happens when D is low? Well, our state transition diagram doesn't tell that. And so that is not a complete state transition diagram. So what should happen if we get a 0? We're in the reset state and we get a 0. Well, that is not any part of our sequence, 1, 0, 0. And so we should just return to the SR state, the reset state, and still keep looking for the first part of our sequence, and specifically the 1 on D, where D equals 1. Okay, now we're done with that state, and we stop thinking about the SR state, and we go to the S1 state. One common error here is that people try to think about all the states at once. You want to think about one state at a time. So in the S1 state, if we're in the S1 state, we know that we've already received a 1. So what happens if we receive another 1? Well, the common error is to say, well, then that's not my sequence, and return to the reset state, SR. But that's incorrect. But that's wrong. So let's suppose we had the sequence 1, 1, 0, 0. Well, here's our first one that would get us, take that transition into S1. And then we'd get that second one, it would take us back to the reset state. And then that 0 would take us back to the reset state, and that 0 would also take us back to the reset state. So we never detected this sequence of 1, 0, 0. So instead of that arc, that transition, we actually want to stay in the S1 state if D is 1. So when D is 1, we want to stay in this S1 state because we've detected the first bit in our sequence, even if it's a repeated group of 1s, potentially could be the first bit in our desired sequence. Okay, so we're done with the S1 state. Now we go to the S10 state. So if we're in the S10 state, that means that we've detected 1 and 0 already. So we know what happens if we get a 0. Well, then we go take this transition and go into the S100 state and assert F. But what happens if we get this, 1, 0, 1? So our next bit, instead of being D low, D is high. Well, again, the tempting thing to do here is to say, okay, well, D is high, not what I wanted, and go back to the reset state. But then we could miss, for example, this sequence. That 1 is potentially the first part of our desired sequence. And so what we actually want to do here is we actually want to go to the S1 state if D is high. So we've gotten the first, if we're in the S10 state, we've gotten the first 1, 0, and if we get a 1, then we go to the S1 state to indicate we found the first bit in our desired sequence, the 1. Okay, and now we look at the last state, S100. Again, we forget about the other states. We don't worry about SR, S1, and S10. We know that if we're in the S100 state, we've received in the previous 3 bits on D, we've seen 1, 0, 0. And so we assert F, but what should happen next? Well, the tempting thing to do here is to do this. Well, go back to reset, start looking for the desired sequence. But remember that a transition happens at each clock edge. So let's show why this is an error. So if we have the sequence 1, 0, 0, so we know that that's what we just had, and next clock edge, Well, we get a new bit, could be a 1, for example. We return to SR, and now we get the next bit. So we've basically missed that bit. We've missed that 1 because we took this transition independent of what D is. And then we get a 0, suppose, on the next clock edge. All right, that takes this transition. And we get a 0. Okay, it takes that transition again. And we've missed that sequence, the 1, 0, 0 sequence there. So what we actually want to do is, if D is 1, we want to go to the S1 state, because that indicates we found the first bit in our sequence, or potentially found our sequence. We found the first bit in that sequence. If we get a 0, though, so again, remember before that we have the 1, 0, 0. The next bit is, if it's 1, we go to the S1 state. But if it's 0, now we can go to the reset state, because we haven't found any part of the next sequence. So if we had 1, 0, 0, we're in the S1, 0, 0 state. Our next bit is 0. Well, that doesn't help at all. That's not any part of the sequence, or the first part of the sequence. We need this to be a 1. And so we return to, in fact, the reset state. So now we can see that our state transition diagram is complete, because it can deterministically knows, given the state, for example, SR, and the inputs, so any input, D or D bar, we know what the next state should be. And here is the state transition diagram drawn out for you. And here we've used the D equals 0 nomenclature instead of D bar, and D equals 1 instead of D. So either one of those works. The next thing we want to do now is to take our state transition diagram and turn it into our state transition table, also called our next state table. And we're basically writing the state transition diagram in table form. So we have the current state, and the input, or inputs, in this case we just have 1, on the left, and the next state on the right. So if our current state is SR, and our input D is low, next state should be SR. Our current state is SR, and D is high, this transition here, next state should be S1. Next one, if we're in S1 here, and D is low, then our next state should be S1, 0. If our current state is S1 and D is high, then we go back to S1. If we're in state S1, 0 and D is low, then we should go to S1, 0, 0. If we're in state S1, 0 and D is high, then we should go to S1. If we're in state S1, 0, 0 and D is low, then we should go to state SR, the reset state. If we're in S1, 0, 0 and D is high, then we should go to S1, state S1. Okay, so now we need to encode our state transition table. This current version is the unencoded state transition table. So we can choose our state bits. So we have 4 states, so we need at least 2 state bits. So let's just choose our encoding. Here we have our state bits, our states, and our state bits. We need 2, so state bit 1 and state bit 0. We can list our states. We have the SR state, the S1 state, the S1, 0 state, and the S1, 0, 0 state. So let's make this 0, 0, 0, 1, 1, 0, and 1, 1. Now we can take these encodings and just translate our state transition table. Again, we have our current state on the left, and our input on the left, and our next state on the right. Okay, so we just take that top row and convert it. SR, we're going to use whatever we have in our encoding down here. Well, it's just 0, 0. D is low, and the next state should be SR, 0, 0. Next row, again SR, but now D is high. Next state should be S1. Encoding is 0, 1 for S1. Next row, we have S1, which is encoded as 0, 1. D is low, next state should be S1, 0. It's encoded as the state bit's 1, 0. Next row, state 1, D is high, next state should be S1. Next row, S1, 0, we've encoded that as 1, 0, D is low, next state should be S1, 0, 0, we've encoded that as 1, 1. S1, 0, state 1, 0, D is high now, next state should be state 1, which we've encoded as 0, 1. Now the last two rows, if we are in state S1, 0, 0, encoded that as 1, 1, D is low, next state should be the reset state. For 1, 1 and D is high, the next state should be state S1, which we've encoded as 0, 1. So here we have the state transition table and the encoded state transition table written out nicely. And now we're just going to take the sum of products form for our next state bits and write equations for those next state bits. So we're going to have two equations because we have two bits of state. And we'll look at, first we'll start with state bit 1 prime. So S1 prime is going to be, well, let's see, there's a 1 here. So it's going to be S1 bar and S0 and D bar. Or, again, sum of products, we're going to find the next one, S1 and S0 bar and D bar. Okay, so we're done with state bit 1, the next state bit 1. And now we're going to write an equation for state bit 0, the next state bit. It's going to be, well, here's a 1, S1 bar and S0 bar and D, or S1 bar, S0, and D, or S1 and S0 bar and D bar, or S1 and S0 bar and D, or the final one, S1, S0, and D. We're going to get D, or, well, we still have this term, S1, S0 bar, and D bar. Okay, and here we have our simplification theorem. D or D bar and something is just going to be equal to D or that something, S1 and S0 bar. And again, you could put that into a K-map and get the same result. So here are our next state equations written out nicely. Now we're going to write an output table. So the output table has the current state on the left and the output or outputs on the right. In this case, we just have a single output, the F output. Common error here is to put the current state and the inputs on the left-hand side of this output table. That is incorrect. So we list our states, SR, S1, S10, and S100. And our output depends only on the current state. If the current state is 100, the output should be high. In all other states, the output should be low. Now we can encode this output table. And we just use our encodings from before, from when we did the next state table. So SR is 00, S1 is 01, S10 is 10, and S100 is 11. And we can write these as our state bits 1 to 0. So again, sum of products, we can see that F is just equal to S1 and S0. So both S1 is high and S0 is high. We'll make F assert to be 1. And here we have it typed out nicely. So now the last step is to take our next state equations, and our output equations. In this case, we have a single output, and we'll turn that into a schematic. So the first thing we do is we draw our state register. We have 2 bits of state, S1 and S0. Remember, S1 It's not the same as state S1. Remember, S sub 1 is a state bit, and S1, big S, big 1, is the name of a state. Okay, so we have our state bits, and we always put a clock into it, and the reset input. Actually, in practice, people forget to hook up their clock or their reset, and their circuit doesn't work, and they don't understand why. So draw our schematic, and then also in practice, remember to always add your clock and reset connections. Okay, then we pull our current state bits around. Remember, on the right side of our flip-flop is our current state. And sometimes I label them here just so I don't forget which one is which. This is S sub 1, and the other one is S sub 0. And then we also bring in our inputs. In this case, we have a single input D. And so now we're going to use the current state and the inputs to determine what the next state should be, given our equations, given our next state equations. And so we start with S1 prime. We're going to have two and-shaped gates, and those are going to be ORed together. And we'll get a bubble here, S1 bar, S0, and D bar. And then the next term, we're going to get S1 and S0 bar and D bar. And now we have for S0 prime, we're going to use that next equation. We're going to have an OR gate. One of its input is tied to D, so D OR. And an AND-shaped gate, one of the inputs is inverted. D OR S1 and S0 bar. So we're done with our next state logic here. And now we need our output logic that is determined just by the current state. And so we're going to look at our equation here, F equals S1 and S0. Look at a single AND gate, S1 and S0.